Okay, the aim of this video is to take you through this glossary of terms from AQA, which deals with lots and lots of different keywords to do with experimentation. So I'm going to try and explain what these different terms mean in the context of an actual experiment. So the experiment is to find out how does the length of a pendulum affect the period. So I've got a pendulum here which can swing backwards and forwards. I'm going to find out how the length of the pendulum affects the time for one swing, which is the period. Now, before I start, I could make a prediction. What do I think is going to happen? So I think as the pendulum gets longer, the time it takes for one swing is going to increase. And that prediction is just based on my experience of pushing kids on swings and stuff like that. There's no real reasoning behind it. It's just, a guess. I could take that prediction further and do a sketch graph. A sketch graph is a simple graph without any scale really on either axis, just to give a rough idea of a relationship. So I might guess, for example, that as the length L of the pendulum increases, the period T of the pendulum increases in a linear fashion. That's a sketch graph. I haven't labelled a scale on each of the axes. It's just a rough indicator of the relationship that I think it might be. We'll see if it is or not. As I explained before, my prediction in this case doesn't really involve a hypothesis. So a hypothesis is sort of a scientific basis for your prediction. If you have some basis in scientific reasoning for why you think your prediction is right, then that would be a hypothesis. Excuse me. In this case, I've got no real scientific reasoning. I'm just basing it on my experience. So I've just got a prediction. But if you had a scientific reasoning behind your prediction, that would be called a hypothesis. Some sort of explanation of what's going on. Now, to find out what's happening, we need to collect some data. Data is either numeric or non-numeric information that you collect and write down. So I'm going to be collecting information about the length of the pendulum and the time it takes to swing. These two variables are my independent and my dependent variables, and you need to be able to identify which one's which. The independent variable is the one that you change. So in this case, I'm going to be changing the length of the pendulum. So that's the independent variable. The dependent variable depends on the thing you change. That's the way I remember it. So the dependent variable depends on the thing you change. The thing that depends on what we're changing is the time it takes to swing. So in this case, the dependent variable is going to be the time. Now, these variables can be either continuous or categoric. So in this case, both the length and the time are continuous variables. That means that they can take any one of a range of values. So the length could be any length. You can vary the length continuously from one length to another. Likewise, the time can vary continuously. There's no discrete chunks. Contrast that with a different type of variable. Perhaps we could try changing the material the pendulum was made from. So we could try aluminium and brass and wood and things like that. That would be a categoric variable. It's not some sort of continuous numeric range. It's just a set of different categories for different materials. Aluminium, brass, wood, glass, whatever. So that would be a categoric variable. Now, if I'm going to do this experiment, I would like it to be a fair test. A fair test means that the only variables that varied were the dependent and the independent variables. Anything else that could change in the experiment has been controlled, and these are called control variables. So in this case, there's a couple of things that I could change that I'm not going to change. So I'm not going to change the thing the pendulum bob is made from. I'm not going to change the mass of the pendulum bob, and I'm also going to try, where possible, to keep the amplitude of the swings the same. So I'm not going to do one with a low amplitude like this and then the next one with a really great big amplitude like this, because that could affect things. So I'm going to try and keep the amplitude the same and the pendulum bob the same as well. Those are my control variables to try and make this a fair test. So the next thing to do is go about actually collecting some data by actually measuring some lengths and measuring some of the periods. The way I'm going to do it, instead of just measuring one period at a time, I'm going to measure 10. So I'm going to let it swing 10 times. So I've got a little marker here, a little pencil, which when I look past the piece of string, it's exactly in line with the piece of string at the moment. I'm going to let this swing and I'm going to start my timer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Disaster strikes. My marker was too close to the pendulum and it hit it. But you get the idea that I'm going to time 10 swings, and then to find the actual period, I can divide by 10. Now, one of the big things on this this sheet is about errors and uncertainties. So this is a good opportunity to talk about that. Let's assume that for this particular length of pendulum and this particular setup, that there is some true value for the period of the pendulum. That means if I did this experiment in an absolutely ideal, perfect way, then there is a correct answer for the period of the pendulum. That would be called the true value. So if I did this perfectly here and timed this perfectly, there would be some correct answer for the period of the pendulum. Now, I've done this already, this experiment, and I've already recorded my data. And I haven't got the same answer every time. So if you have a look down here, here I've timed 10 times the period in seconds, and I've done it for each length in centimetres. I've done it 3 times. And you can see for each of the times I've done it, I haven't necessarily ended up with the same answer, which means that I'm obviously not... Sorry, I've just got to move a bit of paper there. I'm obviously not achieving the true value, because if I was achieving the true value every time, I would have the same answer every time, and I don't. So I've got some sort of error or uncertainty in my measurement of the time. Now, the nature of this timing uncertainty is random, and it's called a random error, because each time I time it, I'm not perfect. Sometimes I accidentally undertime a little bit. Sometimes I accidentally overtime a little bit because I'm not hitting the start and the stop button at exactly the right time. But on average, these values will average out, hopefully, to the true value. So if you've got a random error, where sometimes you overmeasure and sometimes you undermeasure and it's random, if you take lots of measurements and then average them, you tend to get closer to the true value. So that's why I've done this 3 times for each one. Now that's to be contrasted with the other type of error you need to know about, which is a systematic error. So in this case, there's lots of potential sources of systematic error. One potential source of systematic error is a terrible, horrendous human error that could occur but it does happen if you timed it incorrectly. Now, if you notice, when I was counting the swings, I was counting whole swings. Okay, so if I do this again, start 1, 2, 3, 4, 5. I'm counting whole swings. Now, if you accidentally didn't count whole swings, if you counted every time the string passed your marker, if you counted start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, stop. If you counted that way, then every single time you did your measurement, you would find a value for t that was about half the true value. Now, if you did that every single time, and you repeated that 3 times, okay, so you timed it incorrectly here, here, and here, then the result you get when you average is also going to be incorrect. It's going to be half the true value. So this systematic error which is the same type of error that's happening the same way every single time, isn't improved by repeating and averaging. So you could repeat an average as many times as you like using the wrong counting method, and your answer's still going to be wrong. So that's one example of a systematic error. We'll look at other examples of systematic errors in a moment. Now the next key term on the list is precision. Precision is all about, if you take several measurements, how close are they to each other? So here, I'm actually quite pleased with my precision. With the exception of this result here, which we'll talk about in a minute, most of my results are within a few hundredths of a second of each other. So the spread of each of my measurements for each particular length is quite small. So this one's got a spread of about 7/100ths of a second. This one's got a spread of about 3/100ths of a second. So I'm quite pleased with that precision, that variation of my measurements. But that's not to say it couldn't be improved. If I were to use a light gate connected up to a data logger, I imagine a light gate connected up to a data logger would achieve an even greater precision than this. It would probably get all of the measurements to within 1/100th of a second, I would imagine. So there wouldn't be this variation here of 7/100ths of a second. The precision would be much better, because the spread of each of the measurements for each particular length would be much less. So precision is all about the spread of measurements. If you take the same measurement several times and there's a big spread, then you haven't got very good precision. The smaller the spread, the better your precision. However, this is not to be confused with accuracy. So this is quite tricky here. Accuracy is how close your result is to the true value, the ideal value that you would get if you did an ideal experiment. So imagine this. Here, my precision is about, I've got a variation of about 7/100ths of a second. Okay, if I used a data logger, I might improve my precision and get that down to about 100th of a second variation. However, let's say I've used my own manual timing method and I've got this answer. Someone else uses a more precise method, but they do the experiment wrong, and when they use the data logger, they accidentally count half swings instead of whole swings. So the person who used the data logger would have more precision in their measurements, because the variation in the measurements would be much less. But because they had done the experiment wrong and got the data logger to count half swings, their accuracy would be terrible, because the answer they got would be far, far away from the true value, because they've accidentally measured half the time period and not the whole time period. My method here is less precise than using the data logger, but because I've counted correctly, my result is actually more accurate. So the accuracy is how close you are to the true value. The precision is about the variation in each of your measurements for measuring the same thing. So they're not exactly the same. Okay, you can have a really high precision instrument, but if there's a problem with the way you're using it, you might not actually be as accurate as using another method. Okay, so that's quite tricky. Next key term is resolution, which has to do with the instrument you're using. And the resolution is the smallest difference in that particular thing that you're measuring that your instrument can detect. Now, here is, for example, the ruler I'm going to be using to measure the length of the pendulum, and hopefully you can see, well, I don't know if it's not very well in focus, but this is measured in centimetres along here, and it's got graduations every millimetre, so the resolution of this ruler is 1 millimetre. The smallest difference in length that I can really measure with this is 1 millimetre. Right. Here I've got a thermometer, which is totally unrelated to this experiment, but it will just hopefully help illustrate the idea. Not very hard to read, it's not very well focused. However, hopefully you can see that this is graduated here in 10 degrees Celsius on the big scale, and each one of those is divided up into 10. So each one of these small graduations is 1 degree Celsius. So the resolution of this thermometer is 1 degree. That's the smallest difference in temperature that I can realistically hope to detect with this instrument. I could never measure differences of 100th of a degree Celsius with this. It just wouldn't happen. So that's the resolution of the instrument. It's the smallest increment, it's the smallest difference in that quantity that the instrument can detect. Whilst we're talking about instruments, another key term on the list is calibration and what that means. We'll stick with the thermometer here since it's handy and it's a good example. So the thermometer has a scale going up the side of it. This one's going from minus 10 up to 110 degrees C. How did that scale get there? How do we know what's 0, what's 50, what's 90, what's 110 degrees? How is this thermometer calibrated so it gives the right answer, the right measurement in degrees C? Well, different things are calibrated in different ways, but a standard way that people came up with a long time ago for thermometers was to use a couple of known temperatures. So 0 degrees C was defined as the melting point of water, and 100 degrees C was defined as the boiling point of water. So if you put this in ice water and then marked off where the thermometer read, that would give you your 0. If you put it in boiling water and read off where the thermometer reading was, that would be 100. And if you then divided that up into 100 increments, you would have your 100 degrees C calibration. So in order to calibrate it, you've compared it to two known values, a known value for 0 and a known value for 100. So calibration is all about comparing the readings on an instrument to known values so that you can then put those known values onto your instrument. Excuse me. So the thermometer is calibrated by using the freezing point and the melting point of water. Other instruments would be calibrated against other known reference values. Right, so let's get back to the experiment at hand, and we'll just have a quick look at measuring a couple of lengths and have a look at another couple of errors, just so we get a feel for them. So more measurements I need to take are the length of the pendulum. Now here is another opportunity for a systematic error to come up, an error which is not improved by repeating and averaging. So if I'm measuring the length of the pendulum, I should actually be measuring the length to the centre of mass of the pendulum, which is roughly the centre of mass of the pendulum bob. Now let's say I didn't do that, and that every time I measured instead to the top of the pendulum, for example. That would mean that every single measurement for length I did would be wrong. It would be an under-measurement, and it would all be an under-measurement by a certain amount, roughly a centimetre. This is a systematic error which is not improved by repeating and averaging. Okay, I can make this measurement 5 times using this method, and each time I'm going to under-measure because I'm not measuring to the centre of mass, I'm measuring to the wrong place. There's another example, another opportunity here for systematic error again, and it's especially so with the ruler I'm using. Now if you have a look at the ruler I'm using, whoops, nearly knocked the camera over there. If you have a look at the ruler I'm using, the 0 on the scale is here, but there's extra plastic on the end of the ruler here beyond the start of the scale. There's another opportunity for error here. If I accidentally, I'll move this closer so you can see, if I accidentally place the end of the ruler against the starting point rather than the 0 of the scale against the starting point. So if I accidentally put the end of my ruler at the starting point, then I'm going to be under measuring because I'm missing off this bit here. So this is another example of a systematic error. If I do this every single time, measuring it incorrectly, my result is going to be wrong by the same amount every single time, and averaging isn't going to help me. Now this is a specific type of systematic error called a 0 error, which is occurring because the starting point of my measurement is wrong. So the starting point where I should be reading 0 is wrong. You can also get zero errors, well, you can get zero errors with most instruments. You could get a zero error if you were weighing something on some scales. If you'd forgotten to zero the scales beforehand and it had a particular reading, and you did all your measurements with the balance not zeroed, they would all be wrong by the same amount. So that would be a systematic error, and because it was an error in the zero for the instrument, it would be called a zero error. Lovely. So we've taken our data, we've tried where possible to eliminate systematic errors by doing the experiment wrong and by using our instruments incorrectly. And now there's a couple of extra keywords we need to look at in terms of the data we've collected. Next keyword is range, and this one's quite important, especially the way you describe it. So I've taken my data over a range of different lengths. Now, the way they want you to say the range of different lengths, and it kind of makes sense, is to literally give the smallest and the largest value. So the range of my measurements of length was from 10 centimetres to 30 centimetres. That's the range of my measurements. It's not the largest number minus the smallest number. So you might be tempted to think, well, the range of lengths was 20 centimetres because it's from 10 to 30. But this gives you less information. This answer isn't as good, okay? Because if my range was 20 centimetres, that doesn't tell me if I went from 10 to 30 or if I went from 80 to 100 or 1,000 to 1,020 or something like that. This answer gives less information. This answer gives more information. It's better. So if they're asking you for the range of a particular quantity that was used, just say literally the smallest one to the biggest one. That's the range. The interval is an easy idea. In this case, it's the increment that I've gone up in when I've been measuring my lengths. So here I've gone up in 10 centimetres each time, so my interval is 10 centimetres. So two ways to improve an experiment to find out more would be to increase the range, because your conclusions are only really valid in the range that you've actually measured. So here I haven't measured a particularly great range. If I wanted to make my conclusions more robust, I could use a larger range of lengths. So, it wouldn't be out of the question. String's not hard to come by, and meter rulers aren't hard to come by. It wouldn't be out of the question to increase my length up to a meter, for example, with this experiment. There's no reason not to do that. So I could increase the range. The other thing I could do also is decrease the interval. So have a smaller interval, perhaps maybe 5 centimetres between my lengths. That means when I come to plot my graph, I'm going to have far smaller gaps between all my different points. Right, we're getting there, but we've still got a few more terms to go. The next one I'll talk about is whether a measurement is repeatable. Now, a measurement being repeatable means that if you just do the same measurement over and over again, if you repeat the same measurement, you get a similar answer. So I would say my measurements for time here are pretty repeatable. Each time I repeat my measurement, I get a very similar time. 6.47, 6.40, 6.40, 9.00, 9.03, 8.13. Now this result is a bit odd because all the others are within a few hundredths of a second, but this one's clearly way off. So this I would consider to be an anomaly, and ideally I would take that measurement again, but if I haven't got time to take it again, then I won't include that result when calculating an average. Okay, so when I'm averaging these, here I would compute the average of these three numbers and put it in my average. Here, because this one's an anomaly, I'll just average these two and ignore this one from my average. Okay, so getting back to the repeatability thing, if a measurement is repeatable, if you do it several times, you get a similar answer each time. We can then extend the idea of repeating stuff to the entire experiment itself and the conclusions you reach. the entire experiment and its conclusions are reproducible if someone else does the experiment and they reach the same conclusions as you did. So if someone else does the same experiment you did, or even does a similar experiment using slightly different equipment, and they come up with the same results and the same conclusion as you, then that experiment is said to be reproducible. So repeatable is to do with individual measurements with the same person using the same equipment. Reproducible is about the whole experiment being done by someone else and with potentially different equipment and coming up with the same answers. 3 more to go. Validity are your data valid and are your conclusions valid? This has to do with whether you think you've conducted a fair test. So if you're happy that your test has been fair and you have controlled all your control variables and you haven't done anything horrendously wrong, then you would say that your data are valid, and your data would then become evidence. So evidence is valid data that you're happy have been collected well. And this would allow you to draw a valid conclusion, a conclusion that you're happy is based on a fair test and good reasoning. And this, I would say, would be supported, especially if your experiment was reproducible. So if you draw conclusions which you deem to be valid, and then someone else does the experiment, potentially even with slightly different equipment, and they show that your experiment is reproducible, then that would give you real confidence that your conclusion is valid. So I hope that's covered almost all of the terms on the sheet, and I hope it's given you an actual, a real practical example of how these terms are used, and hopefully that should be useful when you come to do your paper 2.